this video. So, welcome to my YouTube channel. So, today's video is going to be very interesting. It is all about how large language models have evolved. I'm going to walk you through the end-to-end process, clear the entire thought process, how the generative AI came in the field of NLP, and take you through the entire history on which the NLP space has evolved from 1980s to 2020. So stay tuned, enjoy this video. If you do like the video, please do subscribe to my channel. I would be posting in more interesting content going forward. So let's get started. So if we just look into the entire pan history of how large language models have evolved. One thing I wanted to highlight what was happening till 1980s or beyond 1980s as well, till 2014. So, as you know, the space has been continuously evolving for sure. It had started with some very heuristic methods, as we all know, bag of words, engrams. Then we kind of there was huge work done in the traditional statistic methods like you have support vector machines, you have naive wires, hidden Markov models. Then significantly researchers were working on word embeddings, then the concept of recurrent neural networks picked up quite well. From there, systems like LSTMs, long short-term memory loss, or GRUs were used to solve complex NLP problems as well. But this was all till 1980 to 2014. Now, if we just switch gears from 2014, in 2014, a very popular white paper came in and it talks about plain vanilla, I call it plain vanilla encoder decoder model, where it has talked how LSTMs can be used in the encoder and decoder model to do language translation tasks in NLP. But things significantly changed in the year 2015 again when something called attention mechanism came. This was kind of an incremental model performance of the vanilla encoder decoder model. The plain vanilla encoder model was kind of transformed with the attention mechanism. But till 2015, with the plain vanilla encoder decoder and the attention mechanism, I think things were going good as well. But the game-breaking white paper, which you all guys know in the field of NLP, was attention is all you need, where the concept of transformer and architecture of transformer came. This was actually a game changer in the field of NLP. So what was happening if you have noticed in the plain vanilla encoder decoder model or attention mechanism was kind of modification of the architecture. But this architecture of transformers is completely out of the box. I think I would say researchers were actually thinking so different. It felt like the researchers have done some kind of time travel. So just to highlight, the transformer model was so powerful because, and I'll tell you the reason why it was so powerful. And again, in year 2018, a very popular white paper called ULM Fit came, which talks about transfer learning, how transfer learning can be actually applied for NLP tasks. That's the ULM Fit white paper which came in 2018. But the things drastically changed from year 2019 to 2020 because that is where people started using both the combination of transformers and transfer learning. Now, when you combine transformers and transfer learning, magic happens. That is where you started building large language models. This was kind of history, and we all know the GPTs, the word, the chat GPTs of the world. This is how the entire history of LLMs were actually large language model, where whatever you call it as generative AI was actually born. But what I'm going to do as we proceed through this video is to break each one of these things, like the encoder decoder model, attention mechanism. We would briefly look into the transformers, we would look into the transfer learning concepts. We will also see how both were used to build the large language models. That's the overall content or the definite agenda we have this for this video. But let's get some concepts clear before we actually dive into the the components which was discussing, starting with the we start with the plain vanilla encoder decoder model, but let's deep dive to some of the concepts and which will help you to recap also your all your concepts. Now, overall idea was for like for your tabular data, right? Which is kind of very structured in a tabular format. Your ANNs were doing a pretty good job in that. If you compare that with traditional machine learning. Now, for your image data, cognitive neural networks were doing a fantastic job. You train them to a large data set, and it starts, interpreting any specific image. You basically fine tune it for your, for any subset of your image data or your custom image data that you have. But the concept of for the sequence to sequence task, RNNs also came into picture, and you know the architecture of RNNs, right? Like how it actually captures the hidden state and takes it forward as we go to the different time steps of an RNN. Like you can see the hidden states like H0, H1, H2, and H3, going forward HT. So you know the concept of RNNs, and you also know the concept of LSTM, long short-term memory loss, or GRUs. Now, we wanted to apply this for some very specific sequence to sequence task. Now, sequence to sequence task is what? It could be anything. It could be machine translation, where you kind of input the machine or the model with a language. I say that my name is Deep, and it converts that to French. You can do specific Q&A task where you ask the model some question, it will answer you back. Or you kind of give a very large text to the model, and the model basically summarizes that. Or you could give the model a time series data and tell the model to predict, what will happen, whatever data you're seeing in present time, what will happen to that data moving forward. That's time series data. So there are a lot of examples of sequence to sequence tasks, but all these things, whatever you would be seeing going forward, starting with the encoder decoder model, these were particularly for the sequence to sequence tasks, like your machine translation. Let's get started with the plain vanilla encoder decoder architecture. Now, to understand this, let me start with a very basic step where we input a sentence on a step-by-step fashion. So, what you are seeing here, there are two main components. One is obviously the encoder, what you see here. Then the decoder. Now, there is also an input sentence which talks my name is T. So you basically input this step by step in forms of embeddings to the encoder. Now you are seeing some blocks of LSTM, right? That is because in the encoder decoder architecture, inside the encoder and the decoder, you have LSTM. The work of the LSTM is to process each and every word, and it maintains the hidden state of that word. Where you see H1, H2, H3, it maintains the hidden state of that word and it moves forward. That's what you're seeing, right? Like this is your H1, H2, H3. That is what it's moving forward. And what it does, what the encoder generates is kind of a uh, uh, summary of the entire sentence is generated as a context vector here. And that context vector is basically fed to the decoder. Inside the decoder, it's all same. Huh? You have again LSTMs, and basically the context vector is kind of a summary of your entire sentence of like my name is this. The context vector summarize the entire sentence in C1, which you call the context vector. Now, the work of the decoder is to, on a step-by-step fashion, it prints the output. Like here in Hindi, it has print Mera naam hai Teeth. Sorry, I don't know any other language apart from English. I know it Hindi. It might be difficult for you to read this, but that is how it processed and it put this to a softmax function. So the main thing to highlight in an encoder decoder architecture is that the summary of the entire sentence which you pass to encoder on a step-by-step fashion is actually taken in by the context vector. That's the plain encoder decoder architecture. See, things were working fine with this. This architecture was fine. Like you see, it was doing a fantastic job doing the translation. But the problem starts with the context vector here because it tends to summarize the entire sentence. Now, imagine if the sentence is of 50 to 60 words or 80 words. Now, the context vector can't retain everything. It will, the context would be lost if the sentence is quite huge. And that is where the problem starts with the encoder decoder model. And that is where encoder decoder model does not do a very good job. That's the reason researchers in 2015, right? They started coming up with the attention mechanism. Let's see what's the overall idea of the attention mechanism. Now, if you see, if you compare these two architectures, right, the encoder decoder model and the attention mechanism, it's architecture wise, it's absolutely the same. You again have encoder here, you have LSTM inside this, you are sending inputs of a sentence on a step-by-step fashion here as well. You have the hidden states H2, H1, H2, H3, H4, and you again kind of send this to the decoder. The major difference between these two models is that you don't send the entire context vector to the decoder. What I am doing here, I don't send the entire context vector to the decoder. What I am doing here is in every decoder step, I send a different context vector, which means my context vector would be would be different for every decoder time step. Let me give you an example how this actually works. Now here, if you see for this particular word, khana, which means food in Hindi, the context vector. So what does the attention mechanism say that to print every word in Hindi, I don't need the entire summary of the sentence. I might need some words or some context from particular words. For example, here in if I want to print khana here in khana here, which is the first word in Hindi, I might need the words the and food only. My context for the other words was good is not basically needed much. That's why you can see I have put in a firm line here from C1 to the, and there's a firm line from C1 to food, and there's a dotted line from to was and good. And same goes with the second word, acha. Acha means good in Hindi. For to print good in Hindi, you don't need the entire sentence. You might be needing this word good from there. That's why you see a firm line from C2. There's a firm line from C2 to good, right? And there's dotted line from all other words. So, long story short, just to summarize this, you're basically the context vector here in attention mechanism is dynamically calculated, which means there is a very simple formula. It's actually kind of the weighted sum of the hidden states of my encoder, and you basically multiply with that attention weights. So if I want to calculate C1, it would be alpha 1, which is the weight assigned to the alpha 2, which is the weight assigned to food, into the hidden state H2, alpha 3 into H3, and alpha 4 into H4. That would be my C1. That is how C1 is calculated. So in attention mechanism, the way your context vector is dynamically calculated, it's kind of a weighted sum of your attention weight, and how it decides the weights, and how it's some deep maths is also within that. But for your brief understanding, it's kind of the weighted sum of your attention weights which you assign to each of the words with your multiplied by your hidden states, which is coming from your encoder. That is how the attention mechanism works. See, attention mechanism does a very good job as well, because here you are passing your context vector dynamically. So it does a pretty good job. You're not sending the entire summary of a sentence in the context vector. That's a major difference between the plain vanilla model where you see encoder decoder architecture. But here, there are some demerits, like this is the attention mechanism. But one major drawback which you would notice in attention is the sequential training. So what is sequential training? Sequential training means you have to pass word by word, like the is passed, the food is passed, was passed. Again, you have to pass good. So it's the training at one time. Basically, you can send only one word to the encoder, and the processing. What happens once you have processed the first word, then only you can send food. Then you send was, then you send good. So the training process, if you notice here, is kind of slow, because you cannot, since the training process is slow, you cannot use this for very huge data sets. And also one thing is major drawback of the attention model is that you cannot apply transfer learning techniques here, because in transfer learning you basically learn from a huge data set, right? Otherwise, this mechanism was working fine, right? It does a pretty good job because you are calculating the context vector dynamically. So if you can't, if the training process is slow, that is because of the sequential training, and you cannot apply transfer learning techniques on top of the attention mechanism. That's the major drawback where researchers had to think different. And that's actually the uh, birth of transformers. When this research paper came, attention is all you need. I hope this is clear. Just keep in mind two things: that how the attention is actually different, and why is different from the plain encoder decoder architecture. Now, going forward, what if you see what is basically transfer learning is you basically apply transfer learning to a huge data set. For example, you apply transfer learning to a huge data set like ImageNet, like it has tons of images. From ImageNet, you basically fine tune it for any particular cat versus dog model, right? That's how you do a cat versus dog image classification. So that is how you apply transfer learning to a variety of tasks. But here, the problem with attention mechanism is that you cannot train attention mechanism on a huge data sets like image, and that's where the problem starts. So we cannot uh, retain we cannot retrain the model, and fine tuning is it's out of box, right? You cannot even think of that. So uh, not applying transfer learning in attention mechanism is a major problem. Now that is where the concept of transformers came, and this is kind of a groundbreaking research paper which happened, right? You all know this research paper. What it says is a very famous research paper. It talks about uh, transformer architecture. But let me actually simplify it for you so that you kind of know what transformers is. So transformer is also even a encoder decoder architecture. You could see here the one marked in green and the one marked in red is basically the decoder. But the major difference between the last two models which we discussed, like the last two models were the plain encoder decoder model and retention measure, is that the components which were inside the encoder and decoder, which were LSTMs, as we have seen before, they were the LSTMs and RNNs were basically replaced by self-attention. That's the major difference between transformers and the previous architecture. But also you could see some new components like you have something called you have residual connections, you have feed forward network here, you have other components like you are doing positional encoding, you are using softmax. So one thing is for sure that it's this particular architecture is very different from the other previous architecture. So you would see that there are a lot of components which kind of interplay here. They were kind of created, and architecture could be trained in parallel. Now, this is the major difference. We need to understand how what is sequential training. So, sequential training was actually done in the plane, in the plain attention mechanism. Now this sequential training was replaced by, you could train this model in parallel, which means you did not send each and every word to the model first. So the training time is much more faster in transformers. That's the reason. And the architecture is kind of highly scalable for transformers, which means you can use it for um, you know any huge data sets, and so which means you can actually apply transfer learning to transformers, and that is where transfer learning was introduced, and you have various models like BERT, GPT from OpenAI, they are all based on transformers. So one thing to note is here in the transform model is that three things to note actually. It's very important for you to understand. Here is that the LSTM inside the encoder and decoder were ditched. They were replaced by self-attention. So with self-attention, they were replaced for the major reason why were they replaced with self-attention is that they could be trained in parallel, which means you can input it with n number of words. You can input 100 words in one sentence as well, and it takes less time to train it. And a lot of small components, like we saw, positional encoding. You have residual connections. All of these small components were used to make this model very stable. Also, last but not the least, is the hyper parameters which were used. They were very stable and robust in this particular architecture. So, one thing I wanted to highlight, if you see the trend, right? If you go backward, like this model, if you see, right, the encoder decoder. Uh, if you see this architecture and attention, right, this is kind of incremental. The researchers have kind of has incrementally changed this architecture to self-attention. They are just the only difference is they are calculating the context vector dynamically from the encoder hidden states. But this one doesn't use anything. The transformers researchers, I think, why is it so significant? They simply came out of mind of this architecture, and this was state in the class architecture because it sometimes feels that this researchers were doing like a time travel and they have designed this architecture. This is so solid and so robust. Like the way they were thinking to build transformers, that was out of box. Because the other ones, right? As I say, it's kind of incremental. It is not incremental. They have not modified the attention mechanism. It's a huge change from attention mechanism. Then let's look into transfer learning. How transfer learning actually works, right? Now, in transfer learning, if you have noticed, you must have heard about transfer learning, right? How so basically the first step, what occurs in transfer learning is that you pre-train your data. Like your data here is kind of pre-trained on a universal data set. It could be any universal data. It could be Wikipedia, IMDs, or any Yelp, or any where you have lot of textual data, sequence to sequence data coming. The main step of step one, where you pre-train your data, is to learn the features of the data set. Now, in transfer learning, basically, whatever knowledge you acquire from the task, task one is kind of reused to boost performance for on a particular related custom task. Let me give an example. If you train your image classification model, you basically give your model the ability to learn about fruit. You basically the knowledge which is gained for to recognize apples, right? If your model knows what apples are, how they actually look like, what is their shape, they would be the model can be used to identify a fruit basket which has a lot of fruits, right? You have apples, oranges, you have pomegranate. That's how your model learns. The second step where you fine tune is that you basically use your previous model. It basically retains the previous weight and the weights in the later layer, right? Here to note that the weights, new weights in your later layer is they are kind of replaced by new weights. And this is where you train your data, you train your model on your custom data set. That's the concept of transfer learning. Now, if you have noticed, transfer learning was not eventually used a lot in NLP tasks before 2018. Uh, that is because of couple of reasons, right? If we look into various NLP tasks, right? You have name entity recognition, you have sentiment analysis, you have parts of speech, you have machine translation, you have text summary, you have Q&A. One thing, if you have noticed, all this tasks like your name entity recognition or your sentiment analysis, all these tasks are quite different from each other because you can't compare name entity recognition with sentiment analysis, right? The general perception of public or the researchers were or the people around were that one particular model should be used for a single task, which means you have one model for name entity recognition, you have one model for sentiment analysis. There was no single model which can do perform all the tasks, and that's the reason till 2018 you must have noticed NLP was not just restricted to computer vision only. The motive of the researchers were to pick one model and train it on various tasks, like one model will do everything you do. sentiment analysis, you'll do parts of speech, machine learning, everything. That is because till 2018, when the ULM fit paper came, right? It was again a groundbreaking research paper. Now they said that whatever pre-training you are doing, they were using machine translation for the pre-training. They said that don't use machine translation. You use something which is called language modeling. Now, what is language modeling? You need to understand that better. Language modeling is nothing but you predict the next word in a sentence. Like, I live in Texas and the capital of Texas is blank. The model will predict the blank should be Dallas. Now, if you see this, you would see that deep, what's the big deal? Like, this anybody can do. No, it is actually a big deal because your language modeling when it happens, right? Um, it's actually learning a variety of things from it. Language modeling actually helps your model to do rich feature selection. Means that see, as I said, the task to predict the next word might sound very simple, but the model is learning a lot of it. It learns grammar. It is understanding the semantics of the sentence. It can derive common sense also. It can derive common sense. I will show you an example how it derives common sense as well. And you can also use this for the variety of tasks. Like I said here, right? All the NLP tasks. You can use language modeling for all of this because your model is learning everything. It's learning the grammar. It's learning the semantics. So you can use it this for a variety of tasks. And the second thing to highlight here in the ULM fit paper, which is a very popular one for transfer learning, is that there was huge availability of data here. Now, you don't need labeled data for this, right? You don't need kind of a pre-training. You can pick up anything. You can pick up a PDF, you can pick up a Wikipedia article, you can pick up a news article, and zero labeling of data sets is needed. It's kind of a unsupervised. So, what does the ULM Fit white paper and transfer learning says? What they did, researchers did, is they kind of introduced a model which was called AWD scheme. And I don't want to get into specific of what is AWD scheme right now, but it was state of the art model at that time. Now, once you kind of feed that particular model to kind of Wikipedia test, this is where the unsupervised pre-training language model works, and you basically change the model output layer. This particular model was kind of fed to Wikipedia, and the output layer of that particular model was replaced to a classifier. And that particular classifier was actually fine-tuned in varieties of data. Like it was given Yelp data, it was given IMDb data, news data, Wikipedia data. And after that, state-of-art result was achieved by the researchers. That is all about the 2LM fit white paper. It's a very famous white paper if you go through this, right, it's called the Universal Language Model Fine Tuning for Test Classification. I'm going to share all this link in the description of the videos so that you guys can go through all the white papers starting from sequence to sequence learning by neural networks. This is the plain vanilla encoder decoder model. This is the neural machine translation by jointly learning to align and translate. This is your attention mechanism. Attention is all you need is nothing but your Transformers white paper, and this one is your ULM fit paper. But the story continues, guys, and the most interesting thing which happened in the history of NLP was researchers combined the transformer architecture with transfer learning, and then the birth of LNP. And this has changed everything in the world of NLP, guys. The GPTs, the birds, Everything has changed by combining the two great architectures of transformers, attention, all you need, transfer learning, ULM straight white paper. Magic happens. LLM was upon. Thank you so much. I hope you enjoy this video. I will do a part two of this video where we will deep dive some more basics of transformers. We would get into some mathematical concepts of attention mechanism, encoder, decoder. But stay tuned. I hope you enjoy this video.